So I believe today, you guys requested a review session for the exam on Wednesday. So what do you want to talk about? Yes, Troy. Ooh, yes, it does indeed. Yep.
We did that. We did
Flip it over. That's literally it. Can you tell me what the expression is, please, so that I can be lazy?
Oh, can I just go up and show you?
Sure.
I don't want to read this off my bad.
It's not that bad. 10 to the 8 s squared plus 10s plus 100 all over 10s plus 10 s plus 1,000 cubed. All right, we're good. Okay, so the first thing that I would want to do is to put this thing into standard form. So I'm going to factor a 100 out of this second term over here. So to me, that's going to give me 10 to the 8 times 10 to the 2 times s squared times s squared over 100 plus s over 10 plus 1. I'm going to pull a factor of 10 out of the 10s plus 10 term. So that's going to look like 10 to the 1 times s plus 1. And then I'm going to pull a factor of 1,000 out from the s plus 1,000 term. So that's going to look like 10 to the 3, but I've got to cube it. So that'll be 10 to the 9. S plus, actually, hold on. S over 1,000 plus 1 quantity cubed. So I can see that I have a 10 to the 8 and a 10 to the 2 makes 10 to the 10. That's going to cancel out the 10 to the 10 in the denominator. So all of those things go away. So let's look at what I have here really quickly. So I have a twice repeated 0 at s is equal to 0. I have a pole at s is equal to 1. And I have a 3 times repeated pole at s is equal to 1,000. And then I have this guy right here, which is a complex conjugate pole. Excuse me, conjugate 0 at omega naught is equal to 10. And if I'm remembering correctly, the damping coefficient comes out to be exactly equal to 1/2, right? So remember from the table that we drew that when we have a damping coefficient of 1/2, that means we don't have to fix anything. Effectively, our straight line approximation is as good as it's going to get. We have no offset, no decibel offset. Isaiah. What? Doesn't everything we're doing is for positive values of, I mean, you're 100% correct that this would be at -1,000, this would be at 1, that one would be at 0, this one would technically be at -10, but it doesn't matter because we're only looking for positive values on our frequency response plot. So let me put all of this stuff together. Let me get my notes because I don't remember what the equation is. I just remembered that I made that specifically so that you wouldn't have to mess with anything. So the expression for zeta let me just do it down here, is b over 2 times the square root of c, where this coefficient right here is b, and this coefficient right here is c. So we would have 10 over 2 times the square root of 100, which is 1/2. Yep. All right. So let me give myself plenty of room here. This might be an aggressive amount of room, but it'll be okay. So I'm gonna put, let's see, I've got some 10 to the 3 stuff going on. Ten to the 0, 10 to the -1, 10 to the -2, 10 to the +1, 10 to the +2, 10 to the 3, 10 to the 4, and there seems like a good thing. Okay, so let's take care of this term first. I wish I had done a different color for that. So I'm gonna do that guy in orange when I put it on the graph so that we can see what the different things that are contributing are. All right, so we have a twice repeated 0 at 0. So remember that means that we cross the axis at s is equal to 1, and we're going to have a slope of positive 40 decibels per decade because it's a repeated 0. Okay. So I guess I should probably put some labels on this thing as well. So -20, -40, and so on and so forth. +20, +40, and so on and so forth. So this is my contribution from my repeated zeros. Then I have my complex conjugate. I'm doing those in blue. So this is effectively just going to look like a repeated simple 0 at omega naught is equal to 10. So it should be 0 until we hit 10 to the 1, and then it should start increasing with a slope of 40 decibels per decade. And of course I drew that incorrectly. That was 20 dB per decade, not 40. Sorry, let me fix that. So just to be clear here, this guy has a slope of plus 40 dB per decade because it's a twice repeated 0. Then our complex conjugate is going to have a slope of 40 dB per decade. Because it's effectively a repeated 0 as well. And it's starting to go up at omega is equal to 10, because this expression right here is s squared over omega naught squared plus s over omega naught plus 1. So omega naught for this guy is 10 to the 1. Then I have my whole at s is equal to 1. So this guy is going to go down at 20 dB per decade, starting at 10 to the 0. Like so. And then lastly, I have my 3 times repeated pole. So that means we're going to decay at negative 60 dB per decade, and that's going to start at 10 to the 3. Yes. So if it's a unrepeated pole, it's minus 20 dB per decade. When it repeats, or every time it repeats, we add 20 dB to it. So if it's doubly repeated, it's negative 40 dB. If it's repeated 3 times, it's negative 60. If it's repeated 4 times, it's negative 80, so on and so forth. That has positive 40. Yep, and yes, because a simple 0 would be plus 20, but because it's repeated twice, it's plus 40. Absolutely right. Yep. Yes, that's why it's at negative 40, or it's increasing at 40 dB per decade. Absolutely. So let's see. So this point right here would be negative 60. And then we would add all of these things together. So let's just do that in maybe this hot pink or something. Okay. So at 10 to the minus 2, we've got a whole bunch of zeros, and then we've got negative 80. So here's 1 point. At 10 to the minus 1, we've got a whole bunch of zeros, and then minus 40. At 10 to the 0, we've got everything is 0, so those add together nicely. At 10 to the 1, we have 40 plus 0 minus 20 looks like positive 20. At 10 to the 2, we have, let's see, so this would be 80 plus 40 is 120. Minus 40 is just going to be positive 80. So 20, 40, 60, 80. At 10 to the 3, let me think about this here. So we got plus 80. And then minus 8. Sorry, let me think about this. So 40, 60, no, excuse me, 40, 80, 120 from our green line. 80 from our blue line would be positive 200. Negative 60 from our purple line. So 200 minus 60 is 140. So wherever the hell 140 is at, somewhere up in here-ish. And then at 10 to the 4, we would have, let's see, 40, 60, no, 40, 80, 120, 160, plus 40, 120 plus 160. Minus 60. Minus 60. So the 120s cancels that out, and it would be at 160, which would be something like that. And then I think it'll just continue at that particular slope. Yes. You're absolutely right. Because we've gone 4 decades past, so you're absolutely correct there. So we'll get rid of this crap. 120 plus 160 minus 80 minus 60 would be positive 140 again. So maybe it will flatten out there. And stay at 140? Yeah. Kobe.
Assuming we're gonna have to draw with these tests,
Yes.
so is this approximation good enough, or do we need to do the 3D?
No, the approximate, for any handwork, I am expecting straight line approximations. Yes. And, for what it's worth, I will provide you with, like a graph paper type thing so that you can, yes.
Where should we look to know where to start our accents? You don't want to start like this.
Right, so like how I sorted mine out was I looked at things, right? So this guy is doing stuff at 10 to the 0, this guy is doing stuff at 10 to the 0, this guy's doing stuff at 10 to the 1, this guy's doing stuff at 10 to the 3. So I gave myself a couple of decades before things started, like my lowest frequency term was 10 to the 0. So just a couple of decades prior to that, just so that we can see what's going on before things kick off there. Walker.
So we're trying to do
Yep.
trying to go by decade, trying to go by decade, or trying to go by time by decade?
So I am adding together the total decibels at each individual frequency. I'm figuring out what the values are by looking at what the slopes were, right? So this 120 right here is the contribution of,
Walk us through it, like.
sure. So let's look at what's going on at something relatively easy. Let's do it at S is equal to 10 to the 1, okay? So at 10 to the 1, our green curve has a value of positive 40 decibels, right? Our blue curve has a value of 0 dB. Our orange curve also has a value of 0 dB. And our purple curve has a value of minus 20 dB. So when we add all of those together, we have positive 20 dB. So that's why I have a point right there on my response graph. And I'm just doing that for every decade, and then I'm just connecting the dots. Toby.
H of S, H of omega, H of J omega.
Whatever floats your boat. They're all the same thing. Like literally, they all mean the exact same thing. If you're using H of J omega, put absolute values on it. But this axis right here is just as equally S as it is omega. Okay.
I'm like, when we define the complexity, I don't define it in how it's supposed to fly the complex on the side.
So a complex pole, let's refresh ourselves here. Okay. So for S is significantly less than omega naught. Get my notes here. Then we have the magnitude of H of J omega is approximately equal to 1, and thus 20 log of the magnitude of H of J omega is 0 dBs. So before we hit our resonant frequency, it's flat. Okay. for S is much greater than omega naught, the magnitude of h of j omega is approximately equal to -1 over, actually, shouldn't be the magnitude. Get rid of those. Not that it particularly matters here. This is going to be omega over omega naught quantity squared. Okay. So this is why it's specifically looking like a twice repeated thing. Okay. Twenty log of h of j omega has a slope of -20 dB. Excuse me, that should be -40 dB per decade because it's twice repeated. Okay. The correction only occurs in the region where omega or S is very, very close to omega naught. Okay. So just to run through that table again really quickly, but this should be in your notes and it's also on a video. If we put our damping coefficient on the left and then 20 log 1 over 2 times our damping coefficient, when we have a damping coefficient of 1, we should get -6.02 decibels of correction. When our damping coefficient is 1/2, we have 0 decibels of correction. When our damping coefficient is 1/4, we have positive 6.02 decibels of correction. Make sure that looks more like a 5 there. For 0.1, we have 13.979 dB of correction. And for 0.05, we have 20 dBs of correction, and so on and so forth. So let's say, just for shits and giggles, we have a complex conjugate pole at, or excuse me, better way to put this would be with omega naught is equal to 10 to the 3 and a damping coefficient of 0.1. Okay. So here's 20 log of h of j omega or s or what I said, whatever the hell you want to call it. It's all the same thing to me. Here is omega or s. Once again, don't care what you call it. It's all the same thing to me. I'm going to put 10 to the 0 here, 10 to the -1, 10 to the +1, 10 to the 2, 10 to the 3, 10 to the 4, and so forth. Okay. So I'm going to do this in red. So, bless you. So we know that our resonant frequency is 10 to the 3. So I would have something like this. So that's my straight line approximation for omega is less than omega naught. Then I'm gonna have my straight line approximation for omega is greater than omega naught, where this point right here corresponds to negative 40 dB. And then I'm also going to add a correction of plus 13 dB right here. And I need to make all of these things true effectively at the same time. So I'm just going to plot that like this. So it's going to jump up, touch this point, and then fall back down and catch up to the minus 40 dB per decade slope. Was that process clear? Yes, Toby.
Let's make it zero. With the green stuff, are they both gonna peak up and then the only difference is that?
So if we had a 0 instead of a pole, this whole graph would be flipped upside down.
But even the peak is there.
Yes. So the whole thing would be rotated upside down, 100%. 13.979 dB. Kara.
There, we have to add that make up.
Yeah, if I give you anything on the exam, having to deal with a complex conjugate pole, I will make damn sure that the damping coefficient is a half so that there is no correction. Yes. Motion.
Are you would be that for the baseline?
So we didn't exactly cover that on the phase plot thing, but effectively it's going to look essentially like just a twice repeated pole or a twice repeated 0. So it's going to hit negative 90 degrees at the resonant frequency instead of negative 45 degrees. And it's still going to transition, start the transition roughly at 1/10 of omega naught and end the transition from 0 to 180 at 10 omega naught. Slope right here is negative 40 dB per decade. So anytime we have a complex conjugate pole that is, so alpha plus J beta times alpha minus J beta, it's that. If we had repeated complex conjugate poles, we'd get into grosser stuff. We won't have repeated complex conjugate poles for sure because your calculators can't do that. Absolutely.
Or the consumer value. It goes off of 10 to 30, so that is 1,000.
Yep. Yep. So we put it in the standard form like this. So this tells me I should start increasing at 100 is 10 to the 2. So I should start increasing at a slope of 40 dB per decade at 10 to the 2. That's what this guy right here tells me. This guy right here tells me I should start decreasing at a slope of 20 dB per decade at 10 to the 0. This guy right here tells me I should start decreasing at a slope of 20 dB per decade at 10 to the 3, but I multiply that slope by a factor of 3 because this is raised to the 3rd power. So that's why we have that minus 60 dB per decade. Did I not do it? Oh, I accidentally, shit, no, sorry, at 10 to the 1. Because this is S squared over omega naught squared. So 100 is omega naught squared, which means omega naught is 10. I'm sorry, I misspoke. Thank you for that. Yep.
Could we look at homework 5, problem 3? I don't want you to solve it, it's gonna take too long, but like, could you briefly describe the process, how you know to solve it?
Extremely similarly to homework 5, problem 1. So let me
rephrase my question. Are you going to give us a problem on the exam that would require us to do all of this?
let me see.
Like, one half of this, yeah. We borrow it.
So on the in-class portion, absolutely not.
Okay.
If anything, on the in-class portion, so let's talk about this really quickly, right? So with regards to your S domain circuit analysis, if I expect you to give me a number, it has to be incredibly trivial. Just because that's the nature of the beast and all of that kind of stuff. So could I have you do the analysis at t is equal to 0 minus and then correctly draw the circuit for t greater than or equal to 0 plus in the S domain and set up your equations as a test question? Absolutely. But I can't make you go through all of the giving me numbers part without it being so simple that you can do it with your calculator because you're obviously not allowed to use your computers. So for problem 1, something like problem 1 would actually be fair game because you can do all of that by hand. Problem 2, not so much. Or excuse me, problem 3, not so much. Problem 2, maybe. But anyway. Yeah. Yep.
If it, so that's what other problems do we have?
I haven't even made it yet, so I genuinely don't even know how many questions that you guys should expect. I think there will be like one circuit analysis question, one setting up things to give me a transfer function, or maybe something so easy that you can actually just figure out the transfer function just using algebra, and then one hand-drawn Bode plot kind of thing. That's my best guess. So 20 points per question. 20 points per question for those 3 questions. And then the take home would be worth 40 points again, like I did last time.
One more question. Did we get the diagram 108?
No, we did not get 108, but we got 212. Yeah, so we will be, send me an email to remind me to tell you guys that, but we will be in ISB 212 on Wednesday for our exam. So you will not be sitting on top of each other quite as much. Hold. Haven't decided yet. Assume the answer is yes.
If you do put a phase on, then we have to worry about 13.97 stuff.
Nope.
No.
When somebody asked about that a moment ago, literally just treat it as if it was a twice repeated pole or a twice repeated zero from a phase perspective. And then also, I'm very specifically, if you get a complex conjugate, it's going to have a 0 dB offset, meaning just give me the straight line graph. I'm going to make sure that it works out that way so that you don't have to worry about that bullshit. Yep. They're already on my YouTube channel. I just haven't put them on Canvas yet.
Can you do problem 5 on the homework sheets? It's taking the graph and going from the graph back to the code.
Sure. So let's look at that really quickly. No, I'll put it on here because I'm just going to talk about it because it's not to be a dick, not that hard. Or I hope it's not that hard.
Wait, they have, I mean.
That is a very, very old sandbox that I was playing around with several years back that I didn't get very far with. Let's see, 224, right? There we go. And then we're talking about homework set number 5, correct? Or 6? Homework 6, problem 5. All right, so let's talk about this really quickly. It looks like I have a constant value of 20 dBs from 10 to the 0 out to 10 to the 1. So that means I must have a constant value of 10 in my transfer function for that to happen. Then I start rolling off at 20 dB per decade. So that means I had a pole at 10. Then I start rolling off at 40 dB per decade. So I had another pole at 10 to the 2. And then it flattens out here at 10 to the 3, so I must have a 0 at 10, or excuse me, a twice repeated 0 at 10 to the 3 to make this thing flatten out. And I'm done.
Okay.
Yep.
Unrelated to the exam, but I don't like the fact that we only have 2 homeworks to go off of for his exam. It's really strange. But how many more homeworks left, or do we have left?
So at present, we are actually rather ahead of where I was when I taught 224 last fall. So I actually only have one more homework generated with solutions and all of that kind of stuff already written out. Do I intend to give you more than one more homework? Absolutely, because we're going to finish up whatchamacallit, resonant circuits, and then we're going to talk about some network theory. And so I need to make at least one homework assignment based on network theory. So my best guess would be 2 to 3 homeworks remaining in the class. And then you also will have a third design project having to do with either Butterworth or Chebyshev filters. I don't remember which, and we'll talk about both Butterworth and Chebyshev filters once we wrap up talking about resonant circuits.
Okay.
So we've got resonant circuits, filters, higher order filters, and then network theory if we have time for it. That's all that's left. Okay.
Put on the syllabus for our projects, you want to write a report and LT Spice.
I definitely want an LT Spice thing. As far as a report, just something telling me what you did and why you made the choices you made, just like circuits do. Do what?
I was looking at the second, I was wondering if that was op amps and you make transfer.
Yes,
LT Spice just be make.
absolutely. I mean,
Flat line from 10 to the 0 to 10 to the first.
Mhm.
Is that 20 decibels achieved by a constant of 20 in the front of the equation?
I think it's a constant 10 in the front of the equation, but yes.
Answer for this homework section, problem 2. Would you recommend doing it by AI, doing great division?
So current division is definitely one way to do it, but you would have to do a source transformation on the practical source on the left-hand side because you have a voltage source and not a current source to start with. I think I personally did it using probably 2 mesh relationships, either 2 mesh relationships or 2 KVL relationships or 2 KCL relationships. I think I probably did mesh because that seems easiest. Because if I'm thinking about applying KCL, I'd have to go here and here, but also here, and that is 3 things to make MathCAD do, whereas mesh is only 2, so I probably just did mesh. I don't know, it's been a year. But if I had to venture a guess, I did mesh. Probably set everything up by hand and then threw it into MathCAD and let it solve for the relationship between V out and V in. Or I out and V in, excuse me. Walker.
Don't know how much that was.
What I just asked you about problem 3.
Like this.
You scroll down, please.
Jackasses. I think I would have to give you something easier than this, to make sure that you have enough time to do it while you're doing the other things, to be clear. So my best expectation will be that you're gonna be doing more setting things up than you are solving things for this upcoming test. And then I might make you solve them for the take-home portion. Toby. I mean, you get an equation sheet. Yeah, absolutely. So your equation sheet, one page front and back, as it has always been. I don't know whether or not you'll actually need it, but I might give you the Laplace sheet as well.
Could we have our equation sheet from last exam back?
Nope. Troy.
To add to that, in the textbook, there's actually like a table with all summarized useless stuff.
Great. I don't even know what textbook you're referring to.
It's just a science text.
I've got like 8 of them. Still don't know which one you're referring to. Copy down the table, go nuts. Handwritten, one page front and back as per usual. Whatever you want to put on there. If you want to put worked out example problems, I do not care. You're turning it in with your test. Caden. Mhm.
Is the, what are your costs for electrical engineers, the class recommendation?
Mhm.
So,
Yes. So for all of you guys who are currently in your junior year, next quarter, you should definitely be taking ELEN 321, ELEN 313, and ELEN 335. If you do not take those classes, chances are you will be here an extra year.
do you recommend, your Bulldog bundle?
Bulldog bundle is a scam. Ocean.
Is it from like 9:30 to 2 nonstop?
Because I have to make it work with me and Amir's schedules. So. Yeah. Yeah, eat a big breakfast. Yeah, bring lunch, whatever. That's a you problem. For what it's worth, I mean, I'm in class from 8 o'clock in the morning until 5 p.m. on Mondays, so. Yes.
You said you have the EOC left to class.
I thought I did. Do I not? Oh, they're all still in draft mode, but I've uploaded them. I'll get that fixed here shortly.
Yeah, this is, I'm ready to. Might get the
All right, now they're no longer draft mode, now they're public. I'll get the links on Canvas set up in a little bit. My apologies for misspeaking. What else? Can I go work on the circuits one test now, please? Okay, later.